Trucks and buses rely on compressed air for braking. The air is stored in cylindrical pressure tanks. Most are made of low-carbon steel and as a consequence are extremely heavy. Obviously, a more suitable material would be lighter, however, remain inexpensive. Here we have conflicting objectives. Light materials that are strong tend to be expensive. We translate the design requirements into the function, constraints and objectives. We then have these three variables. Starting with the mass of the tank, Q, the aspect ratio, is fixed by the dimension requirements. The stress in the wall of the tank caused by the pressure must not exceed the yield strength of the material of the tank wall, i.e., this inequality must be satisfied. We substitute for the thickness a free variable, giving this.
The overall cost is simply the mass
times the cost per kilo of the material, giving this equation, from which the mass and cost relative to that of a low-carbon steel tank can be derived. To get further, we need a penalty function. The relative penalty function z star can be written as this. We evaluate it for alpha star equals 1, meaning weight carries a low cost premium. Low alloy steel has the lower z star, but if we evaluate for alpha star equals 100, where weight carries a large cost premium, carbon fibre reinforced plastic has the lowest z star. We plot both contours of z star on a graph of density over yield strength versus density over yield strength all multiplied by the cost. From these we can infer a trade-off surface. Materials on or near the surface have attractive combinations of mass and cost, several of which are better than the common low-carbon steels. For example, high-carbon steel, low-alloy steel or CFRP.